number theoretic result. I'm not sure if you've heard of normal numbers. Does anyone know what a normal number is?
Is it like the one that like each number has equal number of frequency, like shows up in something like that?
Right, so the normal number depends on the base. So if you look at the decimal expansion, a normal number is one where asymptotically the frequency of each digit is 1/10. Right, asymptotically, not not in a finite number. So if you look at an increasing number of digits and you count the proportion of zeros and ones and twos and nines, they converge to 1/10. That's a normal number in base 10, right? But more generally in base, so let's see, so we have x, for simplicity, let's just take numbers between 0 and 1. So, and choose some k, some integer k greater than equal to 2. Then we write x equals 0.x1, x2, x3, x4 in base k. This is a shorthand basically for x equals x1 over k plus x2 over k squared plus x3 over k cubed. Right? Where each xi is a digit between 0 and k minus 1. This is the base k representation of numbers. Right? So in the case in which k is equal to 10, this is just a standard decimal representation, right? The first digit corresponds to the tenths, the second digit corresponds to the hundreds and the thousands, and so on, right? If it's in base 2, then this is just zeros and ones, and this is 2, 4, 8, and so on, and you get the base 2 representation, base k representation. So you can write the numbers in any base. This is almost unique, right? Except for, like in the as you know, in decimal numbers, there's some points that have two representations, but this is not so relevant for us. Anyway, we say that x is normal in base k, if limit of, it's always the same thing, right? We always have the same thing here. Xi equals j over n is equal to 1 over k for all j between 0 and k minus 1. So each digit occurs with the same frequency, right? So if you look at the decimal here I'm a bit of abusive notation. We're used to using xi as the iterates. Okay, in fact, this would be related to that, but here we're just writing the expansion, so x equals 0.x1, x2, x3, x4. This is the base k expansion, and you look at the base k expansion, you fix some digit j, and you look at the proportion of j, and it converges exactly to 1 over k. This is normal number. So the question is, how many normal numbers are there? And the theorem that we will prove is that the bag almost every x 0, 1 is normal in every base. as you shall see, it is not such a surprising result, but it becomes a bit more surprising when you think that we don't know any example of such a number that is normal in every base. As far as I know, nobody knows. There's no number that you can state which you know is normal in every base. There is no formula that relates the bases, right? So if you know that a number is normal in base 10, there is nothing that tells you whether it's normal in base 9 or base 8 or any other base, as far as I know. So that's very curious. You know, it's the same for irrational numbers. Well, it's not the same. For irrational numbers also, you know, if you just kind of pick a number, it's probably going to be rational, even though almost every number is irrational. But at least there are examples like pi, you know, there's lots of examples of, explicit examples of numbers that we know that are irrational. But here we don't know, I don't think we know. Okay, so why is this a corollary of the ergodicity of Lebesgue measure for piecewise affine full branch maps? What does this have to do with full branch maps? So how do we prove this? Well, first of all, let so first of all, it is sufficient, and this is a little bit cheating writing here. It is of course sufficient to show that that for every base, so let nk is equal to the set of x that are normal in base k, x in 0, 1. Again, I'm just using x in 0, 1 because it's simpler, but obviously this applies for everything, okay? So if we show that, we will show that the Lebesgue measure of nk is equal to 1. And then this is just the intersection. If you take the intersection of all nks, this is the set of points that are normal in every base, right? So then we have that Lebesgue measure of n, which is the set of all normal numbers in every k, is just equal to the Lebesgue measure of the intersection of nk for k greater than or equal to 2, right? And as you know, the countable intersection of sets of full measure has full measure. Okay? So really all we're doing is checking that each base, for the given fixed base, almost every point is normal in that base. The rest looks impressive, but it's just abstract, it's nonsense. So, so let's fix k. So let k greater than or equal to 2. And okay, so in base k, we can divide the intervals into, let's call these I0, I1, I2, up to ik minus 1, right? And this is ik minus 2, right? Then remember that the interval in base k is written like this, x1 over k plus x2 over k squared plus x3 over k cubed, right? And so xi, each xi is between 0 and k minus 1, right? So if you remember what happens in the decimal case is exactly the same. In the decimal case, this is k is equal to 10, right? And we have 10 intervals here. And in the decimal case, this is between 0 and 0.1, between 0.1 and 0.2. So this is also 0.1, 0.2, 0.3. And this here is 0.k minus 1. Point k minus 1 by this point here. This is 0.k minus 2. So you have the same subdivision, right? You have a subdivision where if you write your numbers in base k, then this is what they are. This is 0.1, 0.2 up to 0, k minus 1, and then this is 1 here. Okay? So if you look at the first digit x1, it tells you which of these intervals we belong to, right? So if x1 is 0, then you're going to belong to I0. If x1 is 1, you're going to belong to I1, just like in the decimal expansion, right? So if x1 equal to j, okay, this implies that x belongs to ij. Because what these higher order terms tell you is where you are inside each interval, right? It's again, think of the decimal expansion. These are the hundreds. This comes from 0 to 900s. So according to this, it tells you kind of how much you're adding, but it's always less than the size of this interval. Yeah. Okay, so how does it relate to piecewise affine maps? Well, let's consider the map fx equals kx mod 1. This is equal to f. This is equal to k of x1 over k plus x2 over k squared plus x3 over k cubed and so on. And then when you multiply by k, you get x1 plus x2 over k plus x3 over k squared and so on. Mod 1. Mod 1. And what is this mod 1? Well, here we have an integer part, and here we have a fractional part, right? The equivalent of the decimal part. So this is just equal to x2 over k plus x3 over k squared plus x4 over k cubed, right? And if we write it just in its base k expansion, we can write this as a shorthand 0 dot x2, x3, x4, and so on, right? Where here x is equal to 0 dot x1, x2, x3, and so on. This was the base k representation or expansion of the point x. So always refer back to the decimal case. This is exactly right. What we had in the decimal expansion was exactly the same. When we load this as decimals, right, then when we multiply by 10, what we were really doing is this, right, when we shifted, we're more familiar with the decimal expansion, but so we do it, you know, quickly without having to rewrite it like this. But what we're doing when we say we shift is we're taking out x1 dot decimal expansion, right, and then when we take mod 1, we remove the integer part and we end up with 0 dot something else. So we've shifted, right? So notice that the effect of f is to take the base k expansion and to shift it exactly like when we did the decimal expansion, right? So the effect of applying the map kx mod 1 is very useful when we write these numbers in the base k expansion. Maybe I mentioned something like this right in the very first couple of lectures. So one thing we can do is, by the way, use this to prove the dynamical properties, right? So in this case, you can easily find the fixed points, the periodic points, the dense orbits, right? Everything that we did for 10x mod 1, you can find by using the base k expansion because it is just a shift map. Any questions? Okay. Okay, so what, how is this related? Okay, so now what we know about this map kx mod 1 is that it is a piecewise affine full branch map. So we know that for this map here, because the derivative is k, always, right? It's not only piecewise affine, it's got the same derivative everywhere, piecewise affine full branch, just like nx mod 1. What is the partition? What is the partition on which this is full branch? It is exactly that partition there, right? So you can see that each of these elements gets mapped onto everything, right? Because a point belongs to the partition ij if and only if x1 is equal to j, okay? And if you look at all the points where x1 is equal to j, and you look at the sequences you get after is every single possible sequence, right? So once you fix this, you can get every sequence here. So when you apply the map and you look at the image of ij, I mean, you can look at it in these two ways. You can look at it just graphically. It's easy to see that it's full branch, but I think it's also useful to see it in terms of the formula here, is that when you shift, right, here you get all possible sequences, which means that this map that goes from this interval ij, which you obtain by fixing xi equals j, okay? But then after this j, you have all possible sequences. So this is surjective onto the whole interval 0, 1, right? So you can see both graphically in terms of the graph, but also in terms of the sequence and what it's doing, right? So each ij maps surjectively piecewise affine. So this is a piecewise affine full branch with partition P, okay, with partition P as above. So the big measure is invariant and ergodic. What does that mean about the dynamics? Right? So what can we say then about the dynamics wait, fi of x naught. So wait, what we want is the frequency of visits, right? So we want all the i's between 0 and n such that fi of x belongs to, say, the interval ij. What does this converge to?
A measure?
The measure of ij, right? The Lebesgue measure of ij, because Lebesgue measure, so Lebesgue is ergodic and invariant. And so for mu almost every j, so for, x, for Lebesgue almost every x, we have that this converges to the Lebesgue measure of ij, and the Lebesgue measure of ij is exactly 1 over k, because they all have the same size, these partition elements, these k partition elements. So how do we conclude this? So we know dynamically that, how do we go from this to the base k expansion of the point? Well, we know that fi of x is going to be, if we start with this number here, okay, so the indexing is not ideal. I always get, it's difficult to find a consistent indexing here. So this is really, yes, this is really the same as this. Right, so fi of x is in ij, so when I equals 0, then x is in ij if x1 is equal to j, right? And f of x is in ij if x2 is equal to j, and so on. So every time that you have one of your digits is j, it means that as you keep iterating this map, right? Because then once you start with that, then you iterate again, and you get 0.x3, x4, x5, and so on, and then you iterate again, and you get 0.x4, x5, x6, and so on. So every time in the base k expansion you have j, right? Then after some iterates, when this digit here becomes j, that means that you're inside ij, right? So some iterate being inside ij is exactly the same as the corresponding digit being ij, and so this means that this converges to 1 over k for Lebesgue almost every point, which is what we want to prove. For every j, right? For every j, so for all j between 0 and k minus 1, for Lebesgue almost every point we have this, so we can take, this is a finite, we take the intersection, so for every j there's a set of full measure for which this holds, we do this for every j, we take the intersection, this is just a finite intersection, so we get that for almost every point, this holds for every j. Okay? So this is it. This concludes the proof. This shows that the set of points which are normally in base k have measure a full measure, and therefore almost every point is normal in every base. questions? Okay, so this again, it's curious because the statement itself has nothing to do with dynamics, as you can see, but because the base K representation has nothing to do with dynamics, but even in this very simple piecewise affine case, in fact, because it's piecewise affine, we have this connection with the base K representation of numbers that allows us to prove something like this. Okay, so the third thing I want to do today, but I will just sketch it because to do it properly, we will need to have basically studied a whole previous chapter on topological conjugacy. But I do want to sketch the main ideas because I think they're interesting, and it's to do with constructing more measures. So let me hide the statements. Yeah. So here F and I piecewise affine full branch map. Then it admits an uncountable family mu P, let's say P in 0, 1, of invariant ergodic measures which are non-atomic and mutually singular. So non-atomic means that they do not give positive measure to any points. Right? Like Lebesgue measure is not at every point has zero measure. Probability measures. And mutually singular just means that they live on separate sets, right? So this means that there exists a pairwise disjoint sets, family of sets AP, okay, such that mu P of AP is equal to 1. So they give, so the purpose of this is that I want to broaden a little bit your experience of invariant ergodic measures, because so far we've only seen two kinds of invariant ergodic measures, either on periodic orbits or Lebesgue measure. Okay? Or even later we will see measures that are absolutely continuous with respect to Lebesgue. But these measures are not. They're singular with respect to Lebesgue, except maybe one of them, as we shall see. But they are actually, the support of these measures is the whole interval, as we shall see. So they are a way to further explore the richness of the dynamics that we have in piecewise affine full branch maps. So really, I think it's important to appreciate that there's many more kinds of invariant ergodic measures than just Lebesgue measure or the Dirac delta measures. So the reason why I say is that we need a little bit of background, which I don't want to go because it would take a whole class to do this background carefully, but I think that, so I'm going to sketch the proof of this result just for 2x mod 1. Just for 2x mod 1. But you will see that it's easy to see how it generalizes. So this is 2x mod 1. This is f. And then the way I'm going to do this construction is I'm going to take another family of piecewise expanding maps, piecewise affine, also with two branches, but I'm going to fix the branch in some point P here. So let me call this FP. This is F1 half actually, so this is really in the same family. Here we have a one parameter family of maps depending on P, right? So for every P in the open interval 0, 1, we have a full branch expanding map with two branches. A different one, right? Because when you change P, you get a different map. But Lebesgue measure is invariant in both maps. Okay, so Lebesgue measure is invariant and ergodic for both maps. And the theorem which I'm going to assume, and I'm not going to prove, is that these maps are topologically conjugate. This is topological conjugacy. So if you remember, I talked a little bit about conjugacy, I just briefly mentioned it. So remember that F, let's call them, so maybe I should, to avoid confusion, I should call this G of P, sorry, G of P, and this is F. So F and G are topologically conjugate. If there exists a homomorphism H to I, such that, so every time I have to remember, so the point is that if you apply F and then you apply H, which means H composed with F, is the same thing as applying H and then applying G, which is this. Okay? And this is a homomorphism, right? So the picture, always in mind, of these conjugates is that you take a point X and you take the corresponding point Y, which is G of X, which is H of X. Y equals H of X, right? And then here you apply F, and then here you apply G, G of Y, and G of Y means G of H of X. And you want to make sure that H maps these points to this point, right? So you want also this to be equal to H of F of X. This is the conjugacy that maps orbits to orbits. And it's a homomorphism. So I did not talk about this in great detail, but if you remember, I talked about it being an equivalence relation. And And I also talked about the fact that when you have two maps that are topological conjugacy, you can push forward one measure to another measure, right? And in fact, now I can't remember if we, in the section on ergodic measures, I don't know if we mentioned it, but okay, so in this case we can, so if mu is a measure on X, these are two spaces, sorry, this is more general, this is X and Y, right? If mu is a measure on X, right, then we define H star of mu is a measure on Y, defined by H star mu of a set A. So here we take a set A, and we define this measure to be the mu measure of the pre-image of A. Remember, this is how we define the push forward of measures. We take a measure here, and we push it here in this way. So H star of mu of A is equal to mu of H minus 1 of A. Okay, and then I'm not sure, so I can't remember if I mentioned it or not, but there is a simple lemma which you should do if you've not done it, or should be in the exercises, if H is a topological conjugacy. So this concept you do not need a conjugacy. You just have two spaces, you have a measurable map, you push forward the measure, right? But if H is the conjugacy, it preserves the property of the measures being invariant and of being ergodic. Right? So mu invariant and ergodic if and only if H star of mu invariant and ergodic. So mu is invariant ergodic for F, and H star of mu is invariant and ergodic for G. This is just a simple, it's better than you just check it yourself actually. It's you just use the definition and the definitions of invariance and ergodicity and the conjugacy condition. Okay, and you see that ergodic measures are mapped to ergodic measures. So when you have a conjugacy, topological conjugacy, it is also by measurable conjugacy. You map the measure like this, and the invariance and ergodicity are preserved. So this is a very nice method for constructing measures. So in particular, we can do it here. Okay, so we can define here the push forward of Lebesgue measure. Now this H depends on P, of course, right? Because if you change your P, you change the map here. So the theorem, which we will not prove, okay, is that GP and F of X equals 2X mod 1 are topologically conjugate. Although I will need to tell you something about this conjugacy to be able to understand what I'm going to do. Okay, so we're going to, this is not going to be part of this theorem is not part of the course or of the exam. Okay, we're just assuming this theorem for the sake of this example. So that means you have a topological conjugacy here, and then we can define on here the measure. So this means that HP star of Lebesgue. So let mu P equals by definition H P star of Lebesgue measure. So we take the Lebesgue measure here and we push it forward, which means we take a set here and we give this set a measure that is the Lebesgue measure of its pre-image. So this is ergodic and invariant. It is ergodic and invariant because Lebesgue measures invariant and ergodic for this. Okay, and we just said that the conjugacy preserves ergodicity and invariant. So this measure mu p is ergodic and invariant for f. Right? For f. Because Lebesgue measures invariant and ergodic for g of p. For every p. Okay? So the question is this measure also Lebesgue measure? It could be, right? Because Lebesgue measure is invariant and ergodic here. In fact, what are the measures that we already are familiar with, that we know that are ergodic and invariant for this map? Just those really, as I said, Lebesgue measure and the Dirac delta measures and all the periodic ones. Okay? So, is this Lebesgue measure or is it another measure? And if so, what does it look like? This measure. This is the question. So what's the answer to this? Let's see. For the answer to this, we need to think a little bit about what this conjugacy should look like. Yes? And again, unfortunately, this is a 5 minutes in which we will not give some formal proofs, but I hope to be convincing about this, right? So this is a homomorphism from the interval to itself. So what do you think? So this is a homomorphism. So this is the interval 0, 1. Maps to the interval 0, 1. Right? And it needs to map orbits to orbits. Fixed points to fixed points, periodic points to periodic points. So what do you think, where is it going to map? For example, what's the image of this interval here going to be? Where do you think it's going to map?
0, 9.
That's right. So it needs, again, without going through the formal proof, it's hard to really, give a formal proof of that. But I think it is sufficiently believable that it needs to preserve this branch structure, right? It needs to preserve these branches. So it needs to map 0p to 0, 1/2, and this branch to this other branch. Right? And also, I hope that you can believe that this structure needs to preserve at every scale. So for all the iterates also. Right? Remember that we discussed the fact that if H is conjugate, then it conjugates all the iterates as well. It's easy to see because it maps all the images to the images of the orbits. So if two maps are conjugate, all its iterates are conjugate by the same conjugacy. It's clear. So what does the second iterate of this map here look like? So we just did this in the first part of the lecture, right? We looked at how you construct the partition. What does the second iterate, GP squared? What is the partition associated? So here we have partition P. We have the partition into these two intervals. Right. And here we have, oh, I'm sorry, I'm running late here. Can we have another 5 minutes? if you don't mind, so we'll just finish this. So here we have our original map, right? And then you see that we have here another subinterval that maps to this element of the partition. So this is I0, and this is I1. This is I0, and this is I1. And then I0, this interval here, let's call this interval here I0, 0. And let's call this interval here I0, 1. Right? So this I0, 0 is an interval whose image is I0. Right? And because its image is I0, its second image is the whole thing. Right? And this image here, this interval here, I0, 1, is an interval whose image is I1, and therefore it's I1, so its second image is everything. Right? And then here we have similarly, we have a division, subdivision, I1, 0, and this is I1, 1. Right? So this is an interval where I belongs to I1, its image is in I0, and then it maps to the whole thing, and so on. Yes? I'm sorry for being late. Yes, I will finish very soon. So what does the second image look like? Right? So this means that this interval here, this goes like this, right? This goes like this, and then here we have this interval here that goes like this, and this interval here goes like this. This is the full branch map for the second iterate, right? And similarly, for 2x mod 1, we have the same thing, except that in this case, the original map is just 2x mod 1, and then here you just divide in half again in quarters, right? And then you have okay. So what's happening now to the proportions? I'll just say very heuristically, if we have this conjugacy here, HP, it must conjugate these two maps as well, right? And it must conjugate the corresponding branches as well, right? So not only it must map this branch to this branch, but also within this branch, it must map this piece to this piece, and this piece to this piece, and so on. Right? So it must match up all these pieces. In fact, what you can show is that we can code. So what we really should do is we have a sequence. Let's see, how should I? Let me just maybe state it formally without trying to give too much in the description. Let's say that one of the things you can prove okay, let me put it this way. For 2x mod 1, we know that we have the base 2 representation such that every point has expansion base 2 zeros and ones, okay? But you can construct this representation dynamically. So you can take a point, right, and you look at its orbit, and you construct a sequence of zeros and ones, depending on whether it belongs here and belongs to here, okay? And you can do exactly the same thing here. So you can take a point, and you can construct a symbolic representation of zeros and ones, depending on whether the point is here and whether the point is here, okay? And so every point here has a sequence associated to it of zeros and ones, depending on whether the point belongs to I0, or I1 here, or I0, or I1 here. Okay? So now, by the uniform distribution theorem that we had, we know that in this case, the symbolic representation of the base 2 expansion has exactly 1/2 of zeros and 1/2 of ones for almost every point, right? Because this has measure 1/2, this has measure 1/2, so almost every point will spend half the time here and half the time here. But for this map, also the big measures ergodic and invariant, so almost every point will spend how much time here? Will spend p proportion of time here. Okay, which means that if you look at the symbolic representation of the numbers, the proportion of zeros will be p asymptotically, will not be 1/2. And the last ingredient is that this topological conjugacy preserves the symbolic representation. So all this discussion about the fact that it must map this to this is to say that if you take a point here that spends every time the point falls into this interval, then its image by the conjugacy must fall into this interval. Okay? So this topological conjugacy maps points that have a certain symbolic representation to points that have exactly the same symbolic representation. Right? So this means that here, Lebesgue almost every point, if you look at the symbolic representation, the proportion of zeros will be p. Right? So when you map it by the topological conjugacy, almost every point with respect, it will map to a measure for which almost every point has in its symbolic representation a proportion of zeros which is p. Right? So this means, in this case, the symbolic representation is exactly the base 2 expansion. And we just showed that in the base 2 representation, for Lebesgue almost every point, the proportion of zeros is 1/2. So if p is different from 1/2, then you look here at the set of points where the base 2 representation has asymptotically the proportion of zeros is p, is a set of 0 measure. But it's still a non-trivial uncountable set. Like this is all the points whose base 2 representation, you look at the proportion of zeros and ones, and the proportion of zeros is p. So this measure here lives on this set AP, right, which is the set AP is equal to the set of points x. So in this case, okay, such that the base 2, such that proportion of zeros in the base 2 expansion is p. Okay, and so all these sets are disjoint, of course, because if you look at all the sequence whose proportion of zeros is p, then the proportion of zeros asymptotically cannot be a different value. So these are all disjoint subsets. They're all subsets of Lebesgue measure 0, but they're all uncountable subsets here. They are everywhere, they are dense. Okay, so this measure is a continuous measure in the sense that it's not an atomic measure. The topological support of this measure is the whole thing. Okay, but it lives on an uncountable set which is singular with respect to Lebesgue. Okay, so I'm sorry for going over time, but I just wanted to, again, to really completely prove you need to understand this, the way this topological conjugacy preserves the symbolic dynamics, but I wanted to give you an intuitive idea of the fact that we have these sets and that we have this family of measures that live on these sets, and it's an uncountable family. So the collection of ergodic invariant measures can be really huge in this case, right? It's an uncountable set. It's not just the Lebesgue measure and the Dirac measures on periodic points, but there's lots of other invariant ergodic measures.